This is the first of a two-part video about kinetic molecular theory. The last video was about partial pressures and stoichiometry of gas mixtures. So the main points for these videos are the assumptions of the kinetic molecular theory, the way the theory explains the gas laws we talked about at the beginning of the chapter, and a more quantitative view of molecular velocity in the next video. So kinetic molecular theory is a series of assumptions we make about the way that particles exist and move that help us explain those relationships between pressure and volume and temperature and number of moles that are purely experimentally based. So the kinetic molecular theory is our first look into the microscopic scale about what the molecules are actually doing. This theory assumes gas molecules behave in a certain way, which we will specify. To help explain the experimental gas laws. So all of the relationships that we talked about in the last video between pressure and volume and pressure and temperature, those were relationships that were derived from many, many experiments. And so the assumptions of this theory help explain why those might be true. Now I've cheated and I've written the rules in advance. So if you need to pause the video to get the rule written down, please feel free to do so. So there are 5 assumptions. Here is the first one. So the first assumption says gases are composed of a very large number of extremely small particles in constant random straight line motion. So those particles are extremely small compared to the size of their container, and the way that they move is in straight lines. So they're not moving in curves, they're not moving without a force acting upon them, they're moving in straight lines, and that helps us to model the way that they move in a container. Second assumption, gas molecules are separated by great distances, and the gas is mostly empty space. So in the first one, we said the particles are extremely small, and what we mean by extremely small is much smaller than the distance between two particles. So this is like if there was a football field, there would be one person at the home team field goal and one person at the opposing team field goal. That's how much space there is on a molecular scale between two particles, very, very much larger than the size of a particle. And so because of that, the gas is mostly empty space. The third assumption is that gas pressure results from collisions between the gas molecules and the wall. So in the very first video, we talked about gas as force over area. The force comes from the gas molecules, and the area that they hit is the wall of the container. The gas pressure does not come from gas molecules running into each other. It comes from the molecules impacting the wall. The wall is feeling the pressure of that force. The fourth assumption, gas molecules exert no attractive or repulsive forces on each other or the container walls. So the collisions are elastic. And so elastic collisions, think about pool or billiard balls hitting each other. So one ball hits another ball, the first ball comes to a complete stop, the second ball goes from 0 to full speed and moves off in the right direction. And so there's no attraction and there's no change in the velocity because of that. So no attractive forces and no repulsive forces between anything in the container is what we're going to assume. And we'll see later that this isn't always true, but in order for this to be an ideal gas, we're assuming that these are true. So there's one more. Number 5, the average kinetic energy of gas molecules is proportional to the temperature in Kelvin. This is an important one, particularly to Dr. Debert. This one's clear, near and dear to his heart. The average kinetic energy is proportional to the temperature. So that means if we increase the temperature of the gas, that the particles move faster. They have a higher velocity. They have a higher kinetic energy. And if we decrease the temperature, the particles move on average more slowly. So when you're learning these, it isn't important what the order is. That doesn't matter. And you don't need to memorize these so that you can write this entire paragraph by yourself. But it would be helpful if you could remember a few of these to help you explain why things work. So that was a lot of text that we just covered. And an easier way than remembering all those lines of text is to remember these as pictures. And it's important that you draw the pictures yourself because it's the act of drawing the picture that helps you remember. So let's draw a picture for each of these assumptions to help solidify that in your memory. Okay, so this is going to be for kinetic molecular theory. Number one. So number one said these particles are extremely small and they move in straight line, random motion. So there's our picture of the particles. Number two. Number two said the gas molecules are very small and they're separated by extremely large distances. So the container is mostly empty. They're very far apart. Assumption number three, that one said gas pressure comes from collisions of gas particles with the wall. So we'll draw a gas particle colliding with the wall here and bouncing off. Maybe we'll do another one, colliding and bouncing off. And then we'll draw a pressure gauge. So the pressure comes from the collisions of particles with the wall. Okay, assumption number four, that one said that there were no attractive forces. So that would look like two particles being pulled toward each other. There are none of those, and no repulsive forces, which would mean the particles are being pushed away from each other. No attractive forces and no repulsive forces in our container. And then for point number five, the average kinetic energy is proportional to the temperature. We'll draw a little thermometer here. We'll give it a high temperature. And we'll draw someone who's running super fast. Not sure what your arms look like when you're running, but we'll go for it and we'll give them lots of lines because they're going so fast. And then we'll do a second situation here. We'll give it a low temperature. And we'll draw that person just walking nice and slowly. So higher temperature, higher average kinetic energy, lower temperature, lower kinetic energy. So hopefully those pictures help you remember how this works. So now that we know what the assumptions of the theory are, now we're going to look back at those relationships between the macroscopic variables and try and use our assumptions to help explain them. So we're just going to do a couple of them, and then if you'd like to go through and think about the others in your head, those would be excellent test prep exercises for you to do. So explaining those gas laws with our new kinetic molecular theory. So let's look back at the very first one we talked about from Amonton and Gay-Lussac. So remember that those guys said that pressure was proportional to temperature. So they said as the temperature increases, the pressure of the container increases. And so let's see if we can use those assumptions that we made about the way gas particles exist and move to try and explain them. So the first thing that happens is we increase the temperature. And if we look back at our number 1 through 5 here, number 5 said that as we increase the temperature, the kinetic energy increases as well. So according to number 5, an increase in temperature increases the speed of movement. The particles are moving around faster in the container. And if we assume the volume of the container is constant, that increased speed is going to increase the number of collisions with the walls. The faster you move, the more likely it is that you are going to be hitting the wall of the container. And then as we saw in assumption number 3, gas pressure results from collisions between gas molecules and wall. So that means according to number 3, if pressure is force over area, we are increasing the force from all the collisions, and that increases the pressure. So we started with an increase in temperature, it increased the speed, it increased the collisions, and that increased the pressure. So you don't have to cite the number of the assumption like I did. This just helps me keep track of which parts of the theory I'm using to explain the motion. So that's one way to explain Gay-Lussac using the theory, and that makes it even more believable as a theory. So let's do one more, and I'll leave the rest for you to do at home. So Dalton's law is something we talked about in the last video. That's his law of partial pressures. This said that the pressure, the total pressure of a container with multiple gases in it is equal to the sum of the partial pressures as if they were alone in the container. So this is kind of a difficult one to understand conceptually, that the pressure of gas A alone in the container is the same as the pressure of gas A in the container with gas B. But we can use facets of this theory to think about that. So the first one I'm going to use is the second one. The second assumption says that the gas molecules are separated by great distances and they're mostly empty space. So number 2, molecules are very far apart in the container. And so that what that means is if we add a few more so that is if we mix A and B together in the same container, that shouldn't increase particle collisions. So what makes the situation different between the pressure A exerts in a container by itself and the pressure that A exerts in a container with something else in it, the only difference would be if A and B were hitting each other, because that would cause a change in the pressure. But if these molecules are very far apart, we're thinking like a football field apart from another particle, that means that even if you put one more particle in the container, they would be moving around quickly and they would be hitting the wall the same number of times, but they probably would not run into the other particles. So that means, according to number 3 again, the number of collisions with the wall should match the same as if it was alone. Number of collisions with walls for each component should be the same as if it was alone. So what I'm thinking about in terms of being spaced out, I'm thinking about if I had two 6-year-olds and they were super riled up and full of energy and I needed them to run around in circles and run it out, if I put one of them at one end of a football field and one of them at the other end of a football field, the number of times that they run around and bump into the goal is probably the same number of times alone as if there was another toddler at the other end of the field, because they're so far apart, they're not going to run into each other. They're still probably going to run into things, but they're not going to run into each other because they're very, very far apart. And so Dalton's law says if you have one toddler in a football field versus if you have two toddlers in a football field, you probably have the same contribution from each of them as if they were alone, because they're so far apart that the gases don't affect each other. So think a little bit more about that one and see if you can make sense of it, and check out the PhET simulation for a little bit more playtime with that. Okay, so that's the end of the qualitative video, and the next one will be a quantitative video about molecular velocity.